Okay, so here we are with Unit 2, Lesson 4, and this unit is going to cover a very important topic which is on every single Regents exam that I've ever seen, and that is isotopes. And isotopes is a definition, a term that you should know the definition for. So if you take a look here, the definition for isotope is this part here. Atoms of the same element with different mass numbers. That's the part that you should know. And we're going to look at this stuff underneath here. Now, back in lesson 1, one of the scientists that was mentioned was a guy named John Dalton, and part of his atomic theory was that all atoms of the same element were identical. And basically what he was saying is, and we'll use carbon as an example, is that every single carbon atom that exists is identical to every other carbon atom. It turns out years later that we discovered that that's not necessarily true. They do have some things in common, but they are not identical. And here's an example using carbon. That's the most common one. What they discovered is that when they analyzed the sample of carbon, that not all carbons were identical. There were some carbon atoms that were slightly heavier than other carbon atoms. And they labeled them or named those isotopes. So these are the 3 isotopes of carbon. Many times they don't even talk about carbon-14. They just look at carbon-12 and 13. But we're going to look at all of them. Now, if you remember back to lesson, I think, 2, where they talked about protons, neutrons, and electrons, one of the most important skills in this lesson is being able to determine how many subatomic particles an atom contains. And by subatomic particles, we mean how many protons, neutrons, and electrons does an atom contain. And it's all based on these 2 numbers. This is called the mass number. That's called the atomic number. The mass number tells you the number of protons. And if you have an atom that's neutral, it's also the same as the electrons. The mass number is the protons plus the neutrons. So now if we want to figure out the proton, notice that because they're all carbons, they each have 6 protons. And then 6 electrons. Now, the electrons are not always the same because if you remember from lesson 3, you could have an isotope that is an ion also. But if you look at it, the neutrons you get by subtracting the mass number and the atomic number. So 12 minus 6 gives you 6 neutrons for this isotope. 13 minus 6 gives you 7 neutrons. And 14 minus 6 gives you 8 neutrons. So notice that they have a different mass number, a different number of neutrons, but same protons, and in this case, same electrons. You might want to write that down here, that they have the same protons. They have different neutrons. Those are isotopes. That's how you would describe isotopes. If you take a look at the next one, which is, we're looking at, in this particular case, we're looking at isotopes of the element uranium. And here's the reason why we're looking at this, because if you look at it, just trying to get the mouse down here. Oops, okay. If you look at it, you notice how it's different than the example of carbon that we just did. This is just another way of writing an element's notation. So what they're really saying is that it's 238 is the mass. So you'd have to look up the atomic number, which is 92. And this one would be uranium 240 and 92. So if we go through and do the same thing we did before, it's 92 protons for both. That's why they're both uranium. Electrons would both be 92 because they're both neutral atoms, but they don't really ask you about electrons when it comes to isotopes. And if you subtract this, you're going to get 146 neutrons. And this one, I believe, would be 148 neutrons. So you can see the results come out the same. They have a different number of neutrons, but the same protons, and they have a different mass. So those are 2 examples and 2 ways of writing symbols or isotopic notations, which is how they refer to. Let's look at the problems down here. These are, I believe, looks like questions from previous Regents exams. Remember, they don't really ask you about electrons when it comes to isotopes, so we're not going to worry about that. Let's do the drawing here. Okay, so if you look at it, 2 different isotopes of the same element must contain the same number of, that would be protons. In the above ones, they also have the same electrons, but they don't have to have the same electrons. Number 2, 2 different isotopes of the same element must contain a different, well, we know what's different because we just did it. They have different numbers of neutrons. Now, number 3 is a question that I call a vocabulary question. It's a definition question, but it's not in the form of a definition question, but they're really asking you for the definition of isotope. So if you look at the top of the page that we just started, isotopes of a given element, they have the same atomic number and a different mass number. And that's how you do these questions. So let's move on down to this involves some math, so you're going to need a calculator. Okay. A couple of things to talk about first. First of all, if you look at the periodic table, notice that the masses are not whole numbers. And if you look at the examples we just did, we put the mass of carbon as 12 and the mass of carbon as 13 and also 14. Well, those aren't the actual, those are the masses of those particular isotopes. Then why is the mass of the carbon on the periodic table 12.011? Because if you took those numbers, let me go down here and do this. If you took those numbers, 12 and 13 and 14, and you averaged them out, you would get 13 as the mass. But the mass on the table is nowhere near 13. It's 12.0111. Well, why is the mass then that number? Well, because the masses take into account not only the isotope masses, they also take into account what's called the relative abundance. And if you go back, or if you go down here, what you're going to notice is that we just left out carbon 14 just so there's only a couple of examples. If you take a sample of carbon in nature, almost 99% of all carbon atoms have a mass of 12, and about 1.11% have a mass of 13. So they're not evenly split. So the mass is going to be closer to 12 than it is to 13. And that's one of the questions they ask you about. Instead of just asking you or necessarily asking you to calculate something, they may just give you these numbers, 12 and this percentage, 13 and that percentage, say, well, what do you think the average atomic mass would be closest to? Well, it's going to be closer to the mass that has the higher percentage. So the mass on the periodic table should be closer to 12, and it is. It's 12.011. But what about if they ask you to actually calculate this? So I'm going to show you how to do that. And there's actually two methods for figuring it out. I'm going to show you both, and I think that one is easier than the other, but I'm going to show you how to do both. So the first one, which I think is you're more prone to make a mistake in, is the one that they show here. Here are the two isotopes. They give you this information, and they say, okay, now calculate the average atomic mass for carbon. And it's obviously, it should be close to the one that's on the periodic table. So notice what they did. They take the mass of the isotope, the 12, and then 13. And then notice what they did with the percentage. Here it's 98.89, but they changed it to a decimal form. So what they want you to do is to take the decimal and the percentages and move them 2 places to the left. So you're going to take this decimal, go 2 places, and you now have 0.9889. Multiply that by 12, and you get that number. They want you to do the same thing here. You take the decimal and you move it 2 places, and you put a 0 here. Okay, so you put a 0 there, and you multiply these two numbers. And what you get when you see down here is this number, and that's the mass of the element on the periodic table. Now, how is there a different method? Well, I think the next method is much easier. No worrying about moving the decimal 2 places to the left. You just take the numbers that they give you, the 12 and the 98.89, so I'm going to write it here. 12 times 98.89, and you'll see why I'm putting, I apologize why it keeps doing that, I don't know. You're going to multiply those two numbers, and then you're going to do the same for the other ones. You're going to take the 13 and you're going to multiply it by 1.11, but you're going to add these two numbers. So you're going to multiply these two numbers, you're going to multiply these two numbers, add those two numbers up, and then divide by 100. And you will get the exact same answer. And that's the method that I'm going to go through as we do some examples in class and on the classwork packet. If you choose to do the other method, that's fine also. I just find that there's more likelihood of a mistake. So let's go through and do this one together. I'm not going to go through and do all of them. You can do them in class if you have trouble. So I'm going to do what I think is the easier one. So the first thing I'm going to do is I'm going to take the 10.0130 and I'm going to multiply it by 19.9. And I'm going to do the same thing for the next one, 11.001. 4.93 times 80.1. Now notice that the vast majority of the isotopes have that mass. So when I do my calculation, I know my mass is going to come out to closer to 11 than 10. If it doesn't, I just did something wrong. So then I do those two numbers. I multiply these two, and then I add both of them together, and then I divide that by 100. So I'm just going to take a second here to pause. Alright, so here's what happens. So when you multiply these two numbers, I get 199.258, and you don't have to worry about significant figures. When you multiply these two numbers, you get 881.84493. So I'm going to add those two numbers up and then divide by 100. So what I get for the top number is 1081.1036 divided by 100, and my answer would be 10.811036. That's the average atomic mass of boron. And if you look at the periodic table, it's pretty darn close. I think on the periodic table they only go to the thousandth place. You don't have to worry about rounding off. So that's how you calculate the average atomic mass of an element. Now if you look at the bottom part, and remember I'm trying to keep the videos short, so let's see what we got down here. Again, it's just giving you some more answers, so why don't you make sure that you do these problems right here. And it's just showing you here the difference between the mass number and the atomic mass. The mass number is the mass is just the protons plus the neutrons. The atomic mass, when they use that phrase, that's the average atomic mass of all the isotopes. I think if you just know the mass number, you'd be fine. So that is Unit 2, Lesson 4.